Hello. So this is the first part of the postmortem, in the sense that here in the talk, in the presentation of the Monday session, I was not saying this fully correctly. So what's going on? In the seminar, I was exploring the idea of extending the definition of an integral against. By the way, this is another thing that I wanted to say. There are lecture notes by Terence Tao on differential forms. And at some point I was reading that, and I was finding that it's quite similar to what we are dealing with in Grassmann integrals. And so I'm talking about integrating into a variable. He talks about integrating against a differential form. So, for example, the simplest example that he gives why this is a good notion is that if I have an integral over a curve, for example, in complex plane, then you kind of integrate over the curve, but kind of against the curve, because the curve is selecting where you're integrating there. So here it kind of makes sense to be talking about integrating against a differential form. That's his idea here. And I read the note a long time ago, but I remember that it's an interesting concept for Grassmann numbers, because we are definitely not integrating over an interval, which is just a very special case when we are talking about essentially Riemann sums. So for Grassmann integrals, definitely this is not the right way, and maybe this is a little bit more similar to what we are talking about, and that's why I wanted to be talking about integrating against, for example, Grassmann number GK. Okay, so that's one thing that I didn't do very well in the session, that I actually meant this to be saying against. The reason for this is that I was reading this probably sometime around the pandemic, but then I actually stopped discussing and thinking about Grassmann integrals for quite a long time. And then I remembered that there was this nice way of talking about integrating against the differential form. And here we would be speaking about integration over an interval. So we integrate a function over an interval in Riemann sums, but this is kind of not what we want. So integrating against a Grassmann number, GK. And now our notation here is G1 of L is the complex span of G1 and all the way up until GL, and G1, GI, GJ are anti-commuting, and this is different from GL, which is the full algebra, which is basically generated by G1 of L, those anti-commuting symbols. So now the question is, if I have GK, an integral against the Grassmann number GK, or in general, I could say that I have some Grassmann number, let's call it P, and I'm integrating against that number, then this is a mapping from G1L to C, and this to complex numbers, and this P for any P, for some fixed P, this fixes the mapping to be so G1 of L. So in this case, it's not necessarily a generator, but a fixed linear combination of those generators. So it's in the linear space here. So now this mapping, we were saying it's well defined because we were talking about taking, for example, some generator, some set of generators, and we were showing that this is in this span of GK, where K is from 1 until L. So basically those linear maps parameterized by fixed vectors, so to speak in G1, they give rise to maps, and we found the expression for the linear combination here. So now the question is, how to define the extension of those integrals over any P in this G1 vector space from G1L to the entire Grassmann algebra. Okay, so that's the question that we should be dealing with, and what I'm saying in the talk is not entirely correct.